Okay, so I will present today the seminar about the morphometric analysis of brightest cluster galaxies. This was an article that um, going out this year in September. The presentation will be uh, uh, a little introduction, the objective of the article, the methodology that we use, the morphometric parameters that we use too, some results and some conclusions. Because the article is it's very huge in the results and the conclusions, I will talk just a little bit about the conclusions. I will focus more in the methodology and the morphometric parameters. Okay. This article is about the brightest cluster galaxies, or BCGs. These objects are the most massive and luminous stellar structures in the universe. They usually reside in the densest regions of cluster of galaxies. Usually stays on the center of the gravitational pull, and besides these characteristics, they have more that only have in these objects. Like their major axis tends to be aligned with the large scale distribution of galaxies, and usually they have a loud active galaxy nucleus. So in besides that, uh, they have an extra component that we call envelope that only this type of galaxy possess. So the objective of this article was three. The first one is to investigate if the morphometric indices are a sensible tool to BCG classification. Uh, The second one is to evaluate if and how the behavior of BCGs in the space of morphometric parameters correlate with their stellar masses. The third one is to check how the masses of BCGs from different classes respond to their parent halo masses. For the presentation, I will focus only the first one because if you want to know more, I suggest that you read the article. Okay, it's a nice article. So because I don't have much time to talk about the other two. Okay, the methodology that we apply. The first one we choose two samples of BCGs, one made by von der Linden, the other one by Wen Hanning Liu. The total of BCGs it's around uh, 1,300 BCGs in total. So the first part we download the frames from the science archive from the Sloan. It's a project that are mapping the sky in large scale. Uh, After that, we use the Petrosian radius of the BCGs and in your coordinates to that we obtain from a code called extractor. Then we create a stem from the full image because the full image it's too large. It's take too much time for the program to roll the works. So we cut just the part where the BCGs are in the field. After that, we apply two models. One it's with the program called Galfiti. Then we use like I said two models. One it's for considering that these objects just have just one component that we call a Sersky component. And the other model, it's about the Sersky component plus an exponential component that were the envelope. After that, we use the program Morphometrica. In this program Morphometrica, it's the main program that we use in this article. It's an algorithm developed in Python language that use morphometric parameters to evaluate the BCG. Okay, so what are these morphometric parameters? The morphometric parameters that Morphometrica use are the first one are concentration, C. There are two concentrations indices, C1 and C2. C1 is considering the radii containing 80 and 20% of the galaxy light. The C2, it's another that contain what is inside the radii of 90 and 50%. They after that there are rotation asymmetry, A1. The alongside there are two other asymmetries, the A2 and A3. The the rotation asymmetry it's like we take the original stamp that we create, rotate 180 degrees, and evaluate the residual image. Okay, the A2 and A3 are defined by Pearson and Spearman correlation coefficients. Uh, there are the smoothness coefficient S that measure the small scale structures in the galaxy image. The best example that I have is about if the galaxy possess multiple nuclei. The coefficient G the measures the looks the distribution among the pixels of galaxy image. The entropy of information, the Shannon entropy, H, that are used here to quantify the distribution of pixel values in the image. In the spirality index, that take into account the spiral arms, rings, and bars in galaxies. Okay, these have a little about the emphasis of human-based classification. So, uh, in the results, I like to say before I started,
2 minutes.
okay, that I don't use all. I jump the part of the. I jumped some parts because there are a lot of information. So, when we look how the BCGs behave in the morphometric parameters, we notice that the spirality seems to better discriminate the mergers in the spiral galaxies compared to the rotational symmetry, A1. We use two here, the concentration parameter C2, that is more sensitive to the outer regions of the galaxy. And we choose the concentration C1 as a baseline variable for comparison with C2 in the spirality. We create two graphs mainly. The first one is the plane CC that includes C1 and C2 that you can see above here. That indicates how two profile shapes parameters correlate. And the other is the CS diagram that includes the C1 times the spirality plane. It's the CS diagram is sensitive to the presence of non-elliptical features. So about the CC diagram, we have here the ellipticals galaxies, the CD galaxies that includes the envelopes, the spiral galaxies, the mergers that pass sometimes of fusion. So about the CC diagrams, are this one. With the we can see the elliptical galaxies about BCGs populate a well-defined linear region with some outliers at very low concentration. We can see the CD galaxies, on the other hand, are distributed over a much wider area. Spirals plus S0 galaxies are characterized by C1 and C2 values, a little lower than the E galaxies. The E in the spirality. So for the CS diagram, this one here, we can see the elliptical populate locus very similar to the CD. The CD are more expanded in these graphics. The S, it's a little different from the ECD, and the mergers are totally different from the other three classes. Together with this information, and the parts of simulations that I cut it out from the results here, the main strength of the CS diagrams is allow for an efficient detection of asymmetries. So we use the CS diagram to evaluate the envelopes in the elliptical galaxies here. Inside these two, okay, we made other classifications here that separate the parts of CD galaxies from how much of the envelope they have. When they have an envelope more visible in the image, they walk in the graphic here, and the E galaxies stays in this region here. So from the conclusions, only from this part, we notice that these different classes of BCGs presents consistently, basically, because I don't have time anymore, we can show in this image that we can separate something that it's a human-based classification. Now we can use these graphics to make classification all automatized by a program that frankly doesn't need more the errors from the human-based classification. So thank you very much.
Ok,
Aí, doutor,
thank you.
Desculpa.
Então, perguntas?